Now that we've looked at analysis techniques that we can apply to capacitors and inductors, let's now spend some time looking at some dynamic op-amp circuits. In other words, circuits using op-amps that also contain a capacitor or an inductor. Let's look at a few basic topologies and see what kind of interesting mathematical functions we can do with them. And let's start with what's called an inverting integrator. And here's our inverting integrator. And notice here's our source Vs. Vs, of course, there's an actual voltage source which is not drawn but is implied, which is generating that voltage. Here's our output. And looking at this, this looks very much like the inverting amplifier we looked at before, except the feedback resistor between the output and the inverting input has been replaced with a capacitor, C sub F. So let's go through and let's write the Kcl equation for this and use the IV relationship for capacitors. And let's see what the relationship is between the output and the input voltage. So in this case, we're going to apply the three rules. Got 0 amps flowing into both inputs. I've got 0 volts, the virtual ground. And I've also got a current flowing in from Vs, and that same current I'm going to choose to also flow through C sub F in the same direction. So in this case, let's, I'm going to give a name to this. I'm going to call this current I sub Cf, in other words, the current for the feedback capacitor. And in addition, I'm also going to define, using the passive sign convention, a voltage across that capacitor. I'm going to call that V sub Cf. So let's go ahead and write our Kcl equation. So Kcl tells us that Vs minus 0 over R1 is equal to ICF. It's equal to the current flowing through that capacitor. But I is equal to C dV dt. So therefore, this is equal to Cf times dV Cf dt. So given this expression, let's go and do a little rearranging of terms. If I rearrange terms, what I get is that 1 over R1 times Cf times Vs. So all I've done is I've brought the Cf over to the other side, times dt multiplied by dt on both sides is equal to d VCF. And now we're going to take this and we're going to integrate both sides of this expression. So integrating both sides, I'm going to start with this side and bring it over to the left side here. So I'm going to write this as an integral from VCF T naught to VCF T of dV is equal to integral from T naught to T of 1 over R1 CF times Vs tau d tau. And so what I've just done here is I have substituted and I'm using tau and V as my variables of integration. So now I can go through and of course I'm assuming Vs is a time-dependent function. So instead I called it Vs here I call it Vs of tau to be a little more explicit. So now that I've got this, I can now do this derivative. This is easy, this integral. This integral is very easy to evaluate. This just becomes VCF of T minus VCF T naught. In this case, I'm just going to factor out this 1 over R1 CF. That's a constant. That's equal to 1 over R1 CF times the integral from T naught to T of Vs tau d tau. So here's my expression. I've taken this as far as I can, but let's rearrange a few more terms here. So in this case, I can bring this over to the other side. So VCF of T is equal to 1 over R1 CF integral T naught to T of Vs tau d tau plus VCF T naught. So I've got an expression now for the voltage across the capacitor. Where do I go now? Well, let's look at this. Clearly there's a relationship between VCF and V out. What we see is that 0 minus V out must be equal to VCF. So therefore, minus V out of T must be equal to 1 over R1 CF integral T naught to T of Vs tau d tau minus V out T naught. So this is just equal to minus V out. I substitute. And now I can take this and multiply this entire expression by minus 1. That becomes positive. This becomes negative. This becomes positive. And here is my equation for V out in terms of Vs. So notice what we have here. First of all, this expression on the end, V out T naught, this is the initial condition of the circuit, the initial condition of the integrator at its output. So at T equal T naught, there's our initial condition, which of course is a function of the initial condition across the capacitor itself. And then looking at this, what I see is the output voltage is simply equal to minus 1 over R1 CF times the integral of the input voltage. So I've got a minus R1 CF. This is this 1 over R1 CF. We call this the integrator constant. And because of the minus sign, it's an inverting integrator, hence the name. So I have a circuit here that now performs calculus. Takes an input voltage, integrates the input voltage, multiplies it times a gain constant, a multiplier, and then generates an output voltage. And here's my result. Now, obviously, you think about it, this is pretty interesting because we're actually performing calculus with a very simple circuit. An op amp, a capacitor, and a resistor. Okay, so let's look at a different circuit. Let's keep this one in mind. And I'm going to draw the following circuit. In this case, I'm using an inductor and a resistor. Call this RF. This is L1. And once again, I want to know what is the relationship between V out and Vs. All right, so again in this case, I'm going to apply the three rules. Input currents equal to 0. I've got a virtual ground here at the inverting input. And in this case, once again, I'm going to define currents flowing through the inductor and the resistor. And I'm going to call this one IL1. I'm going to call this VL1 by the passive sign convention across that inductor. And this is VRF, once again, according to the passive sign convention. So given this, what I see is, first of all, by inspection, we note that Vs minus 0 is equal to VL1. So Vs is just equal to VL1. The input voltage is just the voltage across the inductor. Okay? And now I can write an expression for IL1. IL1 is equal to, in this case, 1 over L1, integral from T0 to T of Vs tau d tau, since VL and Vs are the same thing, plus IL1 times T0. And so that's the expression for the current as a function of voltage for the inductor. Then I write my Kcl equation. My Kcl equation is that IL1 is equal to 0 minus V out over RF. So now I can take this expression, substitute for IL1, and what I'll get is the following. So in this case, looking at this, I have that V out is equal to minus RF times IL1, and VCF, pardon me, and then that V out is therefore equal to minus RF over L1 times the integral from T0 to T of Vs tau d tau minus RF times IL1 T0. So I'm just plugging in the value for IL into this expression, and I just rearrange the terms to get it in terms of V out. And then we go through, and I have the RF multiplied here and also here. And to be more explicit, I should say this is actually V out as a function of time, to be more correct. Okay? So from here, we note that IL1 must be equal to IRF. In other words, this current flowing through the resistor, if I call that IRF, clearly IL1 and IRF are the same thing. And so since IL1 is equal to IR sub F, then in that case I can substitute and say that RF times IL1 T0 must be equal to RF times IRF T naught. So substituting the expression for the current, and that's equal to, therefore, VRF T naught. And once again, as before, what we get is that 0 minus V out is equal to VRF, and therefore VRF is equal to minus V out. And so now I can go through and substitute VRF for minus V out, and if I do that, what I'm going to get, I can now eliminate this term here, and therefore what I get is that, or I can substitute that term, and what I get is this. V out of T is now equal to minus RF over L1 integral from T naught to T of Vs tau d tau plus V out T naught. And what do you know? I have another inverting integrator circuit. A different integrator constant. Now instead of it being equal to 1 over RC, it's R over L. Different form. But the fact is, both of these circuits perform the same mathematical function. They both integrate the input voltage and multiply them by a scalar value. Now, here's a question for you. Since both of these circuits do exactly the same thing, is there any reason why we would favor this circuit over this circuit or this one over that one? Well, turns out there's a very good reason. Although functionally both of these circuits can be made to do the same thing, it comes down to economics. Capacitors are much cheaper than inductors. And a capacitor is just two metal plates side by side. An inductor, a good inductor, typically requires winding a coil of some sort. It's not something you can really integrate on an integrated circuit, but capacitors can be placed on integrated circuits. So from a viewpoint of manufacturing to a large scale, capacitors work much better. They're much more economical. So what you're going to find is, even though these are two equivalent circuits from a mathematical point of view, from a viewpoint of practice, we never use the inductor version. We use resistors and capacitors to create circuits like this. Okay. Let's look at a slightly different circuit. Let's take this circuit and let's change some things around. So I'm going to redraw that. Let's redraw that circuit, except now I'm going to flip the position of the capacitor and the inductor. Pardon me, the capacitor and the resistor, excuse me. I'm going to flip their positions. So now instead of the capacitor being here in the feedback, it's in the input leg. Here's Vs, C1, RF, V out. Once again, I'm going to apply the three rules. Input currents are equal to 0. I've got 0 volts on both inputs because the non-inverting input's grounded, so there's my virtual ground. And in this case, this current is IC1, and IC1 is equal to C1 times dVC1 dt, because we note in this case, here's our voltage, VC1 across that capacitor, but VC1 and Vs are the same thing. VC1 must be equal to Vs minus 0 is equal to Vs, and so this is just equal to C1 times dVs dt. which is equal to, draw this current in this direction, that's going to be equal to, by KCl, 0 minus V out divided by RF. And now I can do a little rearranging of terms and rewrite this in terms of V out. And what I get is that V out of T as a function of time is equal to minus RF times C1 times dVs dt. And what do we have here? This is an inverting differentiator. This circuit takes the input signal and takes its derivative. Along the same lines, what if we did this? What if I were to calculate or determine what the output function is in terms of Vs for that circuit? And notice, just like before, I've swapped the resistor and the inductor. And as you might imagine, if you go through and solve for this, what you'll get we can show that V out of T is equal to minus LF over R1 times dVs dt. And so once again, we have an alternative implementation. Both of these are inverting differentiators. And all I did was flip the elements from the previous circuit of the inverting integrator for both of these. Now again, which do we prefer? The resistor and capacitor version. That's much cheaper to implement, although from a mathematical point of view, both circuits can be made to do essentially the same thing, to differentiate. All right? So we can do integration and differentiation, but we can do more than that. Let's look at a slightly more interesting circuit. Let's add some stuff to it. What if we did something like this? What if we did this? So in this case, I've got something that looks familiar. It looks like an inverting summer, except I've replaced that resistor with a capacitor. And so in this case, I can once again go through, pick some current directions. I'm going to call this IC2. So this current and this current must sum to that current. And so by KCl, what I have is that IC2 plus, once again, applying the three rules. This is 0, this is 0. I've got a virtual short circuit at the input. So what I have is equal V1 minus 0 over R1. So this current with this current must sum to that. And so they must be equal to 0 minus V out over RF. And once again, we note that IC2 is going to be equal to C2. This is VC2. So this is equal to C2 times dVC2 dt. But VC2 is just equal to V2. Same voltage. V2 minus 0 is just equal to V2. And so this is equal to C2 times dV2 dt. And therefore I can rearrange some terms, and what I get is that minus V out over RF is equal to V1 over R1 plus C2 times dV2 dt. And now multiplying by RF, what I will get is the following. That V out of T is equal to minus RF over R1 times V1 minus RF C2 times dV2 dt. So this interesting circuit equation here. Notice what I have here. For the V1 input, I just had two resistors. And I wind up with a function with V1 that's nothing more than an inverting amplifier. So I just have an inverting gain here. Over here, for this input, it's got the capacitor and the resistor. That's a differentiation. So here I have an inverting differentiator. So you can see how we can add inputs, and depending upon whether we add in an inductor or a capacitor, pardon me, a resistor or a capacitor, then we can actually get a different function associated with each input. Let's take this idea and go a little further with it. Let me draw this circuit. Let's find V out for this circuit. So here I've got a 2 op amp circuit. I'll give some labels here. C1, R1. And notice I've got two inputs, VS, VC. This input's feeding into both of those capacitors. And the output of this op amp feeds into that capacitor. So for the sake of clarity, I'm going to give a name to this voltage. Call that Vx at the output of the first op amp. Let's go through and let's apply the 3 rules and let's solve for this. Once again, input currents are equal to 0. I've got virtual short circuit at this input, virtual short circuit at this one. Input currents are equal to 0. And so I can look at this and I could start writing equations, Kcl equations for this, but you know, I'm going to do something else. I'm going to kind of look at this from the viewpoint of the different circuit blocks I've already looked at earlier. Let's do something here. I'm going to kind of clarify something here. I'm going to take this Vs and I'm going to break it away and disconnect this. What should I do here? I'm going to take this C3, I'm going to move it up just a little bit here. There's my C3, and I'm going to just redraw this wire. So this is Vs. That's also Vs. So I've simply split this and just created two separate inputs with the same value, just to kind of clarify what's going on. All right? So let's first look at this part of the circuit. Okay, notice what I have here. It's an inverting summer. It's got 3 voltages. 2 of them are going into capacitors, 1 into a resistor. And you know, pretty much by inspection, I can take the same type of equation I just did previously for my circuit, and I can kind of write this out. What I'm going to get is that V out is equal to minus RF1 over R1 times VC minus RF1 times C1 times dVx dt minus RF1 C3 times dVs dt. So I just basically wrote these as differentiation functions and this as a gain function and just kind of plugged them right in the same way I did with that formula there. And now Vx. Vx is equal to, well in this case, that's another differentiator. So Vx is equal to minus RF2 times C2 times dVs dt. And so now I can take this Vx term and I can differentiate it and plug it into that equation over there. And what I will get is the following. What I'll get is that V out is equal to minus RF1 over R1 times VC minus RF1 times C3 times dVs dt plus RF1, RF2, C1, C2 times the second derivative of Vs with respect to time. So plugging that in, I now have a second order differential equation which is implemented by this circuit. So I do 2 differentiations in a row and I see that second order derivative. Okay, this is a circuit that implements a differential equation in real time. Now, today, if we wanted to do a mathematical differentiation, for example, like you're doing in Mathematica on your own computer, what's happening is you've got a computer that is doing all of this using numerical methods. Okay, so it's basically doing differentiation and integration using advanced numerical techniques that are suitable for a computer. But back in the 50s and 60s, there were people looking at what they called analog computers. So instead of doing differentiation and integration and advanced mathematical solutions using a digital computer, because digital computers were incredibly expensive, they were not something that individuals could own. In fact, at best, a very large corporation might own a computer that could do something like this. But analog computers were a way of doing this cheaply. What happened to analog computers? Well, they died out because digital computers became very cheap and very powerful. And so what we saw was analog computers which were very big from like the 1940s all the way into the 1960s just disappeared. I should also point out that this kind of analog computer differential equation computation was actually being done back in World War II. So for example, if you've ever heard of the Norden bomb sight, If you have ever watched an old movie where, you know, people are saying, do we have a firing solution? They're in a submarine and they're going to fire a torpedo, and someone says, do we have a firing solution? What was going on was they were doing analog computing. Of course, they weren't doing it with transistors and op amps. They were doing it with vacuum tube devices and in some cases even electromechanical devices. But what they were doing is what you're seeing here. They were implementing and solving a differential equation in real time where various inputs would tell them, okay, this is where the torpedo is going to hit its target, or this is where the bomb is going to hit its target. So these principles of analog computing actually went way back before we even had transistors or anything like inexpensive integrated circuits or anything like that. This concept really goes back, you know, all the way about 60 to 70 years or more. Nowadays, it's all kind of faded into history, but it's always interesting to kind of bring up a little bit of history and to kind of show everybody where all this stuff came from and where it's going today. All right? So next time we'll close out with just a very quick little kind of qualitative overview of capacitors and inductors and talk more about capacitance and inductance and resistance and how it really affects the real world. And we'll close out with that.